In our previous example, we had 6 lights rated at 7 watts running for 4 hours in a day, a TV of 50 watts running for 8 hours, and a fridge 120 watts running for 12 hours in a day. Our total load will therefore be 42 watts for the lights. Adding that to 50 watts for the TV and 120 watts for the fridge, we will end up with 212 watts. We will take into account the duration we are running each appliance in order to derive the total watt hours. So we have 42 watts by 4 to get 168 watt hours for the lights, 50 by 8 to get 400 watt hours for the TV, and 120 watts by 12 to get 1440 watt hours for the fridge, giving us a total of 2008 watt hours. The size of inverter is determined by the total watts. So in this case, our inverter should be able to support a minimum of 212 watts. To determine the size of the battery bank, we need to work out a solution that will be able to deliver 2008 watt hours per day. In some regions, you may need to provide for 2 to 3 days of autonomy, such that when you have very cloudy days, you will still have enough power to run your appliances. In this case, the required battery capacity will be 2008 watt hours times 2. That is if you're providing for 2 days of autonomy. The recommended depth of discharge for solar batteries is 50 to 60%. In order to ensure that our batteries are not over-discharged, we need to provide for at least twice the battery capacity required. So in this case, the sufficient size of battery bank will be 4016 by 2, which should be 8032 watt hours. Depending on the size of your system, it may be a 12 volt, a 24 volt, or a 48 volt system. To determine the number of batteries in your system, for example, when using a 12 volt to 100 Ah battery, you are going to take the total watt hours, which is the 8032 watt hours, divided by 12 volt and 200 Ah. In this case, the number of batteries will be 4. We now need to determine a solar array that will sufficiently charge our batteries in 1 day. In this region, we get about 6 hours of good sunshine in a day. So the solar array will be determined by taking the 8032 watt hours divided by the 6 hours of sunshine we get in a day, giving us 1338 watts. The size of the charge controller is determined by taking the size of the solar array divided by the system voltage. In this case, we have 1338 watts divided by 12 volts, 12 being the system voltage, which we used earlier in determining the number of batteries. A 120 amps charge controller will be sufficient in this case. However, we can save costs if we increase the system voltage. For instance, if we work with a 24 volt system, our charge controller will be much smaller at 60 amps.